Properties of Liquids, Gases, and Vapors, Part 2, summarizing key exposure and health risk-related chemical properties, narrated by Susan Arnold. The learning objectives of this module are to define key terms and summarize chemical properties of liquids, gases, and vapors that are relevant to human health, exposures, and risks. These chemical properties help us to anticipate and recognize how the chemicals will behave. For example, whether they're likely to evaporate into the air that we breathe and therefore pose an inhalation exposure risk, or whether they're likely to pose a dermal exposure risk because they readily cross the skin barrier. So it's important to understand what these properties are and what they can tell us about a chemical's behavior and potential exposure route that can lead to human health risks. Vapor is the gaseous form of a chemical that is evaporated from a liquid. This image shows water vapor that is evaporated from the lake surface. Chemicals that have the potential to evaporate, forming vapors, are referred to as volatile or semi-volatile. The SI-derived unit for pressure, including vapor pressure, is the pascal. 1 pascal is equal to 0.0075 millimeters of mercury. In this module, we use the units of millimeters of mercury when presenting vapor pressure values. Volatile chemicals, such as the examples shown in this table, have vapor pressures of 0.1 millimeters of mercury or higher at 25 degrees C. They typically have boiling points at or below 220 degrees C. Semi-volatile chemicals typically have vapor pressures between 7.6 times 10 to the minus 13 and 0.09 millimeters of mercury. You can see in this table, benzyl alcohol is at the upper end of this range. Semi-volatile chemicals typically have Henry's law constants in the range of 10 to the minus 4 to 3 times 10 to the minus 8 atmosphere meter cubes per mole. The SI unit for molecular weight is grams per mole. In the table shown here, you can see examples of chemicals and their molecular weights. Lower molecular weight molecules, such as water and isopropanol, tend to have higher vapor pressures and thus are more likely to evaporate into the air, where they can be inhaled, are increasingly associated with respiratory sensitization, and pass through skin more easily, representing dermal exposure risks. The specific gravity is the ratio of a chemical's density to the density of water at a specific temperature and pressure. It's a dimensionless unit that is useful for understanding how a chemical would behave relative to other chemicals. For example, a chemical with a specific gravity of less than 1 will float on the water. Because it floats on the water, it can evaporate into the air above the water surface more readily and present a greater risk of exposure through inhalation than one with a specific gravity greater than 1 and therefore heavier than water. Vapor density is the weight of a gas or vapor relative to the weight of air. It's expressed as a ratio and is therefore dimensionless. Vapor density of a chemical is indicative of whether the vapor cloud will move to a low-lying location, hover, or rise. If a chemical's vapor density is less than 1, it's lighter than air and will rise. When a chemical vapor density is greater than 1, it's heavier than air and will sink to the floor or ground and can pose a fire or explosion hazard and exposure risk. The chemicals shown in this table all have vapor densities greater than 1. Given enough time, would sink to lower-lying locations. The concept of buoyancy as it relates to dispersion that's influenced by temperature, for example, if the vapor is heated, is illustrated in this hot air balloon example. Buoyancy is equal to the weight of displaced fluid, where the fluid in this example is air. When cold air fills the volume of a 4,000 cubic meter balloon, like this one, with an air density of about 1.1 kilograms per meter cubed at 24 degrees C, the balloon displaces about 4,700 kilograms of air mass with a corresponding force of about 47 kilonewtons. The cold air has the same density and force as the air outside the balloon, so it doesn't rise. But as the air in the balloon is heated to a temperature of 104 degrees C, the density of the air is reduced to 0.9 kilograms per meter cubed, and with it, the air mass is also reduced so that it now has an air mass of about 3,700 kilograms and a corresponding force of 37 kilonewtons. The heated air has an upward force of 10 kilonewtons, which is enough to lift a mass of 1,000 kilograms. and that's more than enough to lift the balloon and its burners and carriage and several passengers. As the air in the balloon cools, the density of the air increases and becomes less buoyant, causing the balloon to descend. Partitioning refers to the distribution of molecules between different phases, such as water to air. Partition coefficients are dimensionless units that are useful for understanding how a chemical will partition between two phases when allowed to come to equilibrium. Partition coefficients are determined experimentally and use a variety of different materials. For example, it's often of interest to explore the partition of a chemical between soil and water, as this can explain whether the chemical will be trapped in the soil or released into water. Other materials often used in these tests are air and 1-octanol, where 1-octanol is used to represent human and animal fat. The octanol water partition coefficient is the most common way of expressing the lipophilicity of a compound. That is the physico-chemical property that links solubility, membrane permeability, absorption, and systematic distribution of an agent, such as a chemical contaminant, throughout the body. It's typically expressed logarithmically as log P or log KOW. The correlation between lipophilicity and uptake into the body make it useful for screening chemicals for the potential to penetrate the skin. Chemicals with log KOW values between 0.5 and 3, such as toluene shown in this table, tend to penetrate the skin. The saturated vapor concentration in units of parts per million can be calculated from the vapor pressure and atmospheric pressure using the formula shown here. This is an extremely useful equation for estimating a worst-case airborne concentration from evaporation. A very common scenario is a small spill. Consider the two examples shown here. Imagine a small container stored inside a cabinet spills. In the first example, the liquid in the container is toluene. Toluene has a vapor pressure at room temperature of 28.4 millimeters of mercury and is classified as a volatile chemical. If the chemical evaporated such that the cabinet concentration reached equilibrium, the saturated vapor concentration would be, worst case, 37,368 parts per million. This would be concerning not only from a health hazard perspective, as it exceeds the occupational exposure limit by a factor of 1,500, but also as a flammability risk. In the second example, the semi-volatile chemical is decanol. Decanol has a much lower vapor pressure of 0.08 millimeters of mercury at room temperature. Under similar conditions as example 1, that saturated vapor concentration would reach 10.52 parts per million. Decanol has an OEL of 10 parts per million, so while the saturated vapor concentration would be much lower relative to toluene, it could still be a health hazard in this scenario. This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.